in my last video, I explained you about availability, that what is availability, and what all about Markov diagrams, Markov chains, how to draw the chain, and how to draw the table, all about that. So we have discussed the starting things. Now we'll go into further detail that what happen when we have a series system, or when we have two components, two items working together in series. Now in this video I'm going to talk about the series system. So you can see that here we have a series system, that is, okay, here's the pencil. We have a start point, end point, and A and A. These are two components or two items that are connected in series. So how we are going to draw the chain, and what about the tables? Let's have a look how it's gonna work. The same thing happens here, that we have a working state, the failure state, but we also have a access state. Now what is access state? This access state is simply x is a random variable, that is, when we are going from one state to another state, we have a random variable in between. So when we are not in the working state and not in the failed state, so what happens then? It is because you know that in series system, when one component failed, the overall system failed. So to prevent that happening, we have to place a variable x, random variable x, just to prevent this happening, because we don't want to make our whole system fail. So that's why it's in series, and in series we have to place an x. And remember, and here we have one person on repair. Okay, so what happens when one person is on repair? Okay, now we have w t plus delta t x. Here we have wt, we have the working state, the failed state, it's same as before, the working state, failed state, and what is gone for addition here, that is the x. Here we have a random variable x, because we are talking about now the two components. When we are talking about two components, no matter they are in series or parallel or whatever, remember that when we are talking about two components, we have added one more component, we have to go for x. Here we have the x here. So here we have added the random variable, and the same is that this random variable will go from t to t plus delta t as before the transition state. I have told you that for w t plus delta t and f t plus delta t, they were going from t to delta t, step by step transition was happening. Same is here. So what happens when we are in the working state? Suppose our item is in the working state. When it is in the working state, so that means that there is no chance of getting that item failed, because it's new. It's just like as new, as good as new. So no chance of getting that item or that system to be failed. So there is no chance of failure rate, no chance of failing. So 1 minus lambda delta t. Okay, this is the same as in the series. It's just that we have put a square here because we have two components working. Yeah, we are talking about two components, that's why we have put the square here. Okay, and what's next? This is how it gets. It's just that okay, I'll tell you afterwards. Let's talk about this thing. And what is this? This is the failed state. Here we have the failed state. What is the failed state? Failed state is that when the system, when an element, when a component, when an item is failed, has been failed. Okay, so it's failed and it needs to be repaired. You know, it's when it's failed, it needs to be repaired. but first we have to write the thing that is when it is failed. So when it is failed, we wrote it as lambda square delta t square, because right now it is the item is failed. It's no repairing conditions, nothing else is provided to it. It's just that its initial condition is it has failed. So lambda square delta t square, and y square is here because we are talking about two items. So first the working condition when there were items that were good, that were new, so they were good, they were in one working condition, so no failure rate, no failure rate. So that's why it was 1 minus lambda, and here it is lambda square delta t square, because in the failing condition, in the failing part, the item has both the items has failed. So when they are failed, so that's why failure rate and delta t, we put failure rate here because they have failed. Okay, now next let's move to the next thing. Leave this x here. Now we talk about the failure rate. You remember here we always talked about the repairing, that what is the procedure to repair, what is the possibility to repair it. In the first part, we talk about the working condition and the failed condition. We talk about working one, when it is working, so this thing, and when it is failed, so this thing, like we did before, as you remember, where it is, yeah, here it's same is in the when we were talking about the one component, the only one component was present here also. When we were in the working condition, see, when we were in the working condition, it's 1 minus lambda because there's no failure rate, and when we got to the failed condition, it's lambda delta t, so our item has failed. And in the other part, what we did in the other part, we were here to repair it. We took it from here to here. First we go from here to here, and then we took it from here to here, from fail to work condition, just when we are in the procedure of repairing that item. So when we were repairing it, working to working and failure. So when we were repairing it, suppose when we have the item here, when we have our item here, when we are in the failed condition, so no repairing thing, there's nothing like repairing thing, so nothing should be repaired, the item cannot be repaired, so 1 minus mu is the repair rate, delta t. And when it goes from here to here, when from failed condition it goes to working condition, it's been repaired, so we wrote it as repair rate into delta t. This was for the one component thing. Now we are talking about the two components thing, but everything is the same. It's just you can see that we only have the we only have square here. In the first part we only write it as square. So what's next? Now here, as we wrote before, it was in the repair condition. Okay, we are in the mode of repairing condition. First I will tell that when it's in the failed condition, the item has got failed, so what would be the repair rate? When the item has got failed, it can't be repaired, so it would be 1 minus mu delta t. See, 1 minus mu delta t, like the same that was here, 1 minus mu delta t. So it's in the failed state, it's completely failed and it cannot be repaired, so 1 minus mu is repair rate, so it cannot be repaired. This becomes the failed state. And whole square because we are here talking about the two components, so that's why we wrote it like this. And what's next? Now here what we wrote in the series, we go from failed state to the working state, but here we can't go from the failed state to the working state. First we have to see this thing, we have to see this x thing, we have to see why we have to see this x thing, because in series we can't go from failed state to the working state, because if one component failed, so the whole system in series, the whole system is failed. So first we have to work on our one component, then we can go in the work state. We cannot directly go into the work state, from failed state to work state, because we don't know that which component, which item is failed. So first we have to see that which component has failed, we have to work on that component, and then we can go to the working state. So we cannot go directly to the working state from failed state to the working state. That's why this thing is 0. This is a new thing, this is different, because we have a series thing, we have a series combination. So that's why we have 0 here. Okay, now what remains is this x part and this middle part, this thing, the column and the middle row. These things are remaining. I hope that others are being clear to you, right? And how we got this? How we got this? Well, how it comes? So by see, x is a random variable, so we have to find the value for the x. Okay, it's just easy. It's not something, anything from far away, from behind, from very far. It's just in the equation, in the same thing. Okay, so it's not that difficult. It has come from this thing, see, and we have to find the value for x. X is a random variable and we have to find out its value. So how we are going to find out? We will take this whole square and we are going to solve it. See, this is for first one, we are taking this first one, we have to find this value. What we took, we take this 1 minus lambda delta t whole square plus y. This y is because we need to find the value. We need to find the value of x. So that's why for finding the value of x, we keep here this y equals to 1. Why equals to 1? Because the reason that we have put it equals to 1, because we always said that this whole part, this part and this part, is equals to 1 when we solve them, right? Remember in the series, remember when we were when I told you about the one component thing, when we have the one component only, I didn't remember to mention this, that the sum of this thing and this thing should be equal to 1. And that's a technique, that also is a trick, that you can find your table as correct, either it's correct or not, by just adding these things, this row and this row. When you add these things, you will get the answer as 1. So when you get the answer as 1 is equals to 1, so that means that your table and the elements and the values that you have kept inside are correct. So let's have a look. 1 minus lambda delta t plus lambda delta t. So lambda delta t and this lambda delta t goes away, and what is left behind? This 1. So it means that our values are correct. And same here, mu delta t plus 1 minus mu delta t, mu delta t goes away, and what it remains? 1. So it means that our table, the inside values of our table are correct, because we are getting the answer of 1. So now let's see here. So that's why it is the rule of this Markov chain, Markov theory, that it is equal to this thing equals to 1. So let's see, either it is 1 or not. Okay, so that's why we have kept here that we will see that either it is 1 or not in afterwards. Now first we have to find this x thing, we have to find the value for this x. So equals to 1, that's why we keep it as 1. Okay, now we open the whole square. So 1 1s are 1 minus 2 lambda delta t plus lambda square delta t square plus y equals to 1. This 1 and 1 comes here and it becomes minus, these goes away. And what we got now is y got there. Oh sorry, these values got there, and when they got there, their signs obviously change. So when they change, it becomes 2 lambda delta t minus lambda delta t square. So this is the value for our x, that we name it as y. Clear? Sorry, this one. It is this. This is the value 2 lambda delta t minus lambda square delta t square, 2 lambda delta t minus lambda square delta t square. So we have got the conclusion. We have got the answer for our one term. It's just the one thing left. Others are left. Still others are left. And you know what? This is also the same. This thing will come from here. As we see that we can't do for 0 because it's 0. We can't take it, and we can solve this. So here we have solved it. 1 minus mu delta t whole square plus y same equals to 1. We open the whole term, we have opened the square of this term, and 1 goes away. What the value for y comes? 2 mu delta t minus mu square delta t square. So this is the required value, and here it is. So what is written here? Where mu square delta t square, this, I think this square is missing here. Yeah, mu square delta t square and lambda square delta t square, yeah, it is here, is small. They are very small, so they can be negligible. Okay, so what we assumed that this delta t square, mu square delta t square and lambda square delta t square are really small, so we can keep it as 0. We can neglect them. So where are these terms? It's here, it's here, it's here, and it would be here also when we solve it. So it would also be here. So there are four times they would be negligible and they would be 0. Okay. And it would also be here as when we will solve it. So lambda square delta t square, lambda square delta t square, lambda square delta t square, and this is clear. Mu square delta t square and mu square delta t square. So negligible, 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 and negligible. So all that goes away. So okay, how many terms now we have? Find for our table. We have 1, 2, 3, 4, 5, 6. 6 terms are gone. 6 times 6 terms are okay, they have been done. So now let's take this x1, our random variable x. So when we are in the working state, we are here in our working state. When we are our working state, so it means that our one component, it goes failed. When we are in our working state, one component goes failed. So it means that this component goes failed. This is our one component, it goes failed. So when it goes failed, we need to get it repaired. So that's why from working to repair condition, one component repair condition. Okay, we have two components, so it would go, as I told you, it will go step by step. When because we don't know that either which one is going to repair, which one has damaged. So that's why from working to repair condition. So repair rate lambda t, mu is the repair rate. Yeah, and when we let's take it afterwards in the failed condition, and we are in the failed condition. So we also don't know that which item has failed. But when we are in the failed condition, we have to go for the repaired thing. But right now we are in the failed condition, so that's why failure rate to lambda delta t. We will keep it like this and this, because here we are in the repaired condition, going to repair our item. Here our item has failed. Okay, so it's in middle. Okay, and what's this now? We are here in between. See, x on the above and x on the corner, x and x. So that it means that we are in between, in middle. So what happens when we are in middle? We are not in the working state and not in the failed state. We are in middle. We are in middle of something. We are in middle. So we are not in the working state and not in the failed state. So that's why it would be 1 minus lambda delta t minus mu. That is, this is mu. You can see that. Yeah, it zooms clearly. It's not blurred. 1 minus lambda delta t minus mu delta t. Sorry for my writing, it's a little weird. So we have find out all our 9 terms. These all 9 terms are okay. And the theory that I told you, that either they are equal to 1 or not. So let's see either they are equal to 1 or not. Yeah, first see this one. Afterwards we'll see the square ones. First see mu delta t plus 1 minus lambda delta t minus mu delta t plus lambda delta t plus lambda delta t minus lambda delta t goes away, minus mu delta t plus lambda plus mu delta t goes away, and what remains? 1. So oh, this is correct. That means, so we can write it here equals to 1. So this middle thing goes correct. Yeah. And now the upper one. What is the upper one? Okay, what is the result for the upper one? Let's have a look. We have to solve it. One more thing, I told you that this is negligible, so this is negligible, this is negligible, yeah, this is negligible, and it would also come here mu square delta t square, that would also be negligible, and here it would be lambda square delta t square, that would also be negligible. So here 3 are negligible, here 2 are negligibles. So when we neglect the other thing, what we got now, see, when we neglect this thing, see, you can see that when we neglect this, we neglect it to 0. What remains? 1 minus 2 lambda delta t. Okay, this thing here and 2 lambda delta t here. So plus 2 lambda delta t minus 2 lambda delta t, they goes away, and what remains here? 1. So this is also correct, it's 1. Yeah, and this has been done. Now that this one, we have neglect this, we have neglect here mu square delta t square, so 2 mu delta t 1 minus 2 mu delta t. Okay, so this goes away, and think that 2 mu delta t, okay, I'll 2 mu delta t and 2 mu delta t. So this and this goes away, what remains? 1. So this is also correct, which means that all our 3 possibilities are correct because they are equal to 1. You can see this. Yeah, there they are equal to 1. So we have got the correct equations, the correct forms. So you can also check it by this, that either they are correct or not, by doing this simple thing. It's really easy. Okay, now let's just move forward and just hurry up the things, as it's all the same as in the series. If you, oh sorry, I said every time my mouth is going it for series, I'm so sorry for that. Okay, now rest is the same. It's all the equations are the same that we did before. I have explained them in the last video of when we were having one component, so they were a really bit. I have explained them at extreme, so you can go from there. Okay, so pw t plus delta t, we are now in the state we have to put these values in the form of probability. So we keep it pw t plus delta t. When we are talking about this in the probability of the working state, so we will take all these 3 values. So we took all these 3 values, 1 minus 2, sorry about my writing, sometimes I am also unable to understand sorry, 1 minus 2 lambda delta t. Here it is 1 minus 2 lambda delta t, and remember lambda square delta t square is negligible, so from this thing we will got only this, and this is we are talking in the working state, so probability of working state, and the other is plus mu delta t, and we are talking about the x state, random variable state, so px of t, this we name it as equation 1. Now for the x state, random variable state, what is, we neglect this, 2 lambda delta t, see 2 lambda delta t, and we are in the working state, so pwt plus 1 minus lambda delta t minus mu delta t. Okay, and it is in the x state, so px of probability of x of t plus what's next, this is negligible, it remains 2 mu delta t, and it is in the f state, failed state, so pf of t. I hope you can see it clearly, 2 mu delta t and pf of t. So this is finished. Now this thing, what it is now, okay, you can without seeing from the notes, you can say it back with me also. Remember mu square delta t square we have neglected, so this is 0, so we don't have to write this. Okay, so it this will become lambda delta t and in the x state, so lambda delta t px of t, and here mu square delta t square was negligible, so 1 minus 2 mu delta t in the field state, p probability of pf of t. So let's see, yeah, lambda delta t px of t plus 1 minus 2 mu delta t pf of t in the failed state. So this was for pf1 and we named it as equation 3, and we also have, okay, oh, it's not mentioned, oh no, I have written it here, we named it as equation 2, this is equation 1 and this is equation 3, right? Okay, now we say that we are talking about equation 1 implies that, this is the sign for implies that, and pwt plus delta t equals to, okay, so for this you have to see it behind what's happening. Yeah, we are working on equation 1, so pw of t, this multiply, simple multiplication, 1 multiply by pw of t minus 2 lambda delta t pw of t plus this will remain the same. So where it is, this will remain the same, yeah, pw of t minus 2, okay, yeah, it is the same. You can do it by yourself, simple multiplication and nothing else. Okay, now we are working on, first we are working on equation 1. So remember what we did before, we brought this pw of t here, so it becomes minus and this remains the same as here, and delta t are in the both terms, so it would come outside and would be in common, and then this delta t will goes down. I have missed that step. I know that everybody can do it, it's a really simple step. So delta t is common, it comes out, and this thing delta t goes down there, so it remains like this. And what we say now we are taking equation 2. Okay, so what was equation 2, remember, it's the most lengthy equation. So here also what we have to work, yeah, we have to multiply this px of t with 1, this px of t with this, and this px of t with this, so we have to open the bracket. So it's just we have done this simple multiplication and nothing has gone changed, so you don't need to get worried about it. See, this we multiply by this, this 3 terms have got px of t, it's a increasing thing, plus this, everything is same. Now the same the only one px of t, I mean to say the separate px of t comes here to the left hand side of the equation, and rest remains the same, and delta t brings out common outside, and this delta t goes down there, and everything is the same. And one more thing, that by doing all this part, we name this equation as equation 4 and this equation as equation 5. And the same is for equation 3, you know that. Equation 3, remember this thing, here also we have to multiply this pf of t by 1 and this 2 mu delta t p of t, this goes multiplication, so it's just happening here and nothing else. Okay, this multiplies and this multiplies and this pf of t will come here to the next opposite side of the equation, and the rest remains the same, and the delta t comes out in common and this delta t will goes here, and we named it as equation 6. So you have to name the equations very clearly and very, you know, you need to concentrate on this, that what equations you are naming and what do you have to do on these equations. Next, 4, 5 and 6 we have named them as in this way 6. Now what we have to do, remember we took the derivative of equation 4, 5, 6. So we have find all these things, this, and now we are in the process of taking the derivative of 4, 5 and 6. So when we took the derivative, you know, this dot is the derivative for derivative. When we took the derivative at time t, so this pwt plus this remains as it is, and this delta t goes away. See, and here also this in equation 5, this becomes the derivative px dot of t. This remains the same and this delta t goes away. This is the method for doing the derivative. You know, you must be knowing how to take the derivative, and this is equation 6, and the same delta t goes away and the rest remains the same, and now pf dot of t. So we have find out 3 equations by taking out our derivative. And what we are saying now, at starting conditions, we say that starting condition, when we have no working state, no the access state, no the failure state, so equals to 0. Starting conditions are that all these 3 equations are equal to 0. So when we bring them as equal to 0, when we keep these things as equal to 0, I hope that it is clear and things are not getting blurred. Okay, by the way, I'll take the pictures. I'll be taking the pictures of these notes and would be sending you the link in the description. I've kept the link in the description. I'll be keeping the link in the description so you can go and see them from there also. Okay, these are little topics, and literally I'll be posting 2 or 3 pictures for this, so you can go and take a look from there, and you can save those pictures. That would be really advantageous for you. So we have put these things as 0, 0, 0, 0, right? These things become 0. Initial conditions, we got them as 0. Rest remains the, this is px of t. We took it as common. We bring it common because it was more making our equation lengthy, so we brought it outside, and this lambda plus mu comes here and bracket close. So this is just this way, and rest is 2 mu pf of t. This, okay, we named it as 7 and we named this as 8, and rest, this one becomes 0, and we also see, is it clear? Lambda px of t minus 2 mu pf of t. It's the sorry, it's the same. So we name this one as 7 and this one is 8. Why we are doing all these things? Because we need to find out the value for Pw of t. Remember, so that we can consider Pw of t as a of t or a of infinity and so on. So that's why we are doing things like this. In the last video, when we have only one component, we took the Laplace and Laplace transform and Laplace inverse, remember, to find out our value. But in this we see that our equations can easily be solved by substituting them. So we are going to do the substitution. I hope you all know about substitution. So what we do now, we say that we name them as 7 and 8. right? I hope everything is clear. So we named it as 7 and 8. We say that take equation 7. When we take equation 7, so it is minus 2 lambda p w of t plus mu px of t. This is equation 7 and it goes here and it goes here. So we need to find, we need to got the pw of t value, and we have to remove all other ones like px and pf. So how we can substitute to just get the pw of t? So this equation is a perfect one for finding pw of t. What we have to do, we have to find the value for px of t and we have to find the value for pf of t, so that in the form of pw of t and pw of t, so that we can put the values of these two and then we will be easily finding our pw of t. So let's see how we are going to do this. We took the equation 7. This was a really small equation, and from this equation we can find out we can find the value for px of t. See, is it everything is clear? So px of t, how we find out the value? This it goes there on the next side, and minus minus got cancelled, and px of t, this mu comes here in division, and the value for px of t becomes 2 lambda pw of t over mu. What we say, keep it in equation 8. So I told you no that we are going to take equation 8 and we will put the values of px of t and pf of t in equation 8. So now we have find first value, that is px of t. See, so we are going to keep it here and rest remain the same. See, the others are the same, and see, these are the same, just the px of t is something like this, it comes here, and rest is the same. I hope everything is clear to you. Equals to 0 because this is all is equals to 0, so that's why equals to 0. Okay, now we have found out these. What is next? What we are talking about next, that our first we talk about our starting conditions. We take these all to 0. Now we are talking about the other conditions. What would be the next conditions of our theorem? That pw of t plus px of t plus pf of t equals to 1. Now we are saying that all these threes are equal to 1. You know why we are saying this? Because we have proven by our table also that, remember that when we are saying that this plus this equals to 1, so this is w, x and f, they are equal to 1. All these are getting summed up and they are equal to 1. So that was our theorem, that is the rule for this table. So it's just that we have wrote this here where it is. Okay, we have wrote this as the same as we said it before, that pw of t, px of t and pf of t is equals to 1, just as this. So what is the advantage for doing that? That here we will find out the value for, we have found the value for px of t. Now what is remain? Pf of t is remaining, so we will got the value for pf of t. How we are going to know? See, what we did, by doing this, we keep the value for px of t here, okay, and rest remains the same. And what is happening? Okay, this mu got here and multiplied. Okay, this comes here plus it goes there in minus pf of t, and okay, it goes there pf of t, it remains as it is, right? Oh, sorry, it's, don't just get confused, there's nothing so weird about it, it's just that yeah, nothing is so weird. Sorry for the disturbing line. Yeah, so it's just that this u goes, this is the LCM thing only, this u goes there and the rest remains the same. It's just that I haven't kept this u over here, it was gone, so that's just I was just correcting this thing, so I have corrected. Now mu remains the same, now rest remains the same, and you can see that by this pw of t is a common here, so it comes out, and what remains after, mu plus 2 lambda over mu, and rest remains the same. And now what's gonna happen, pw, okay, what's next now? Yeah, we have to find the value of pf of t, no? Okay, so this, okay, this mu and mu comes in cancellation, mu over mu, so what it remains, 1. See, this 1 remains, and next this mu goes away, so 1 remains, and this 2 lambda over mu, it remains the same, so 1 plus 2 lambda over mu, and rest are the same. Rest is the, see, pw of t, it's the same, so this comes here. And what's next, we want to know the value for pf of t. Okay, we want to know the value for pf of t. Sorry for the paper, it's a little weird. Okay, we know the value for pf of t, we know the value for pf of t. So this one is irritating here, so this one will go there. Yeah, no, so this one will not go there. This, I think this pf of t is going there. Yeah, pf of t goes there, so when it goes there, it was in minus, it comes in plus. Okay, it comes in plus here, equals to, this one remains the same, and it was here, remember this pw of t, this thing was here, so it will come here in the minus, in the form of minus. This was here plus, so it will come here in the form of minus. So when it comes here, 1 plus 2 lambda mu over 2 lambda over mu pw of t. Everything is clear now? So it's just that this one remains here, and this pf of t goes there, and this thing comes here. So you know now that we have to find the value for pf of t. So this is what we got. Okay, now next rest, what we can't do anything with this. So we have got the value for pf of t, that is this 1 minus bracket 1 plus 2 lambda over mu pw of t. So what we are saying now, keep values of px of t and pf of t in equation 8. Okay, so our work is done now. This we have to go for equation 8. We have got the pw of t is the same, we have got the value for px of t, that is this, and we have got the value for pf of t, that is this, and just we are going to keep these values in the equation number 8, and nothing is so complicating here, nothing is gonna complicate. So see, we have kept the values, we have put there here, and nothing else, we have kept everything in sequence. Yeah, you can do it by yourself. I hope that it won't be, you know, nothing is gonna irritate you, nothing is gonna be complicated for you. You can do it by yourself also, it's nothing else, just simple multiplication, division, minus, addition and subtraction, and nothing else. It's just a calculation, simple mathematics and all. Okay, so what we are going now to do, this remains the same, we are not touching it now. What we are going to do, okay, first we will see that what mass, you know, so we will do the brackets first. 2 lambda lambda square pw of t plus 2 lambda mu pw of t over mu, bracket closed, and rest remains the same, nothing changes, rest remains the same, nothing is changing here. Yeah, I think there is a little one plus 2 lambda over mu. We have a plus here, and we have kept it as minus here. Okay, so we'll keep it 1. Yeah, that is as it is, as before it was, we'll keep it as 1, as plus, sorry. Yeah, everything is clear till here. Now we are going this, for this 2 mu remains the same, 1 minus 1 plus 2 lambda mu pw of t equals to 0. Okay, first we have take these things. If we are going for the BODMAS, that's why. And what's next? See, here we see that pw of t is here, 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 and here also, but first we are going to go for these. So we take these as common. Okay, pw of t we took it as common. 2 lambda remains the same minus 2 lambda square over mu. This is over mu here, yeah, and 2 lambda mu. So this mu and this mu, they both up and down, so they got cancelled out. So that's why 2 lambda only remains 2 lambda, right? So rest is plus 2 mu minus how this 2 mu comes, plus 2 mu plus 2 lambda plus 2 mu minus 2 mu. Okay, yeah, this is in bracket, so we are going to multiply this 2 mu with all of these. So 2 mu got multiplied with 1, 2 mu got multiplied with this, so 2 mu comes here, and this is being solved, mu minus, okay, we are here for, we can write it as minus plus minus 2 lambda over mu, and this is down here, this is going LCM, and pw of t equals to 0. This remains as the same, right? And what's the next step? Let's see. Okay, this is the same, 2 lambda minus 2 lambda square over mu plus 2 lambda minus 2 mu square. This multiplied with this, and where it goes, you must be thinking where it goes. So we have keep it, because we all these terms are in the form of pw of t. They are in common of p or w of t, but only this form is the thing that is the different one. So we take it to the other side of the equation. So it is it comes here in minus 2 mu, and rest remain the same. Minus comes here, 2 mu into 2 mu, 2 mu multiplied by mu, 2 mu square, minus yeah, sorry, minus, yeah, obviously we have solved it in the beginning, so it would be 2 multiplied by 2 to the 4 lambda mu, 4 lambda mu. Don't think that this minus, why these minus are not positive, it's just that we have solved them before. See, where it was 1 plus 2 lambda over mu, it was like this. So we solved it before, we keep it as minus and minus plus minus, so we have solved it. It's just that we have wrote it here, we have solved it, yeah. So this is not going to solve it again, obviously. 2 mu square minus 4 lambda to the 4 lambda mu over mu. This mu comes here, and this remains here, and pw of t, now we have seen that only this thing was remaining, so we take it as to the opposite side, and this pw of t also comes in. This whole equation becomes now the common for the whole equation becomes together in the common, as we take the common of pw of t from them. So they have become together now. And what is this? This thing remains there, this remains there, this is the same, and okay, this goes there, and we multiply this and we multiply this, so this thing comes here. Okay, this is okay. Now the next step, this remains the same, this remains the same, you can see that. Is it clear? This remains the same, and this mu divided by this mu, so it becomes only minus 2 mu. This mu cancel out with this mu, it becomes only 4 minus 4 lambda, and rest is the same, right? Okay, so plus 2 lambda plus 2 lambda, 4 lambda minus 2 lambda square over mu minus 2 mu minus 4 lambda. So this goes away and this goes away in positive and negative. This remains, let's see, this thing here and this thing here. Okay, so okay, it's here pw of t. Now we are going, we will keep this the thing that were multiplying with pw of t over there. We will take them to the right hand side, and when you take them up to the right hand side, what happens? See, these things go like this: 2 lambda minus 2 lambda square over mu minus 2 mu. Just it's the same, nothing goes different. And what's happening, I hope you can see it. Yeah, now it is clear. Okay, so what's happening? Yeah, it's just we are taking this minus sign outside, so it becomes plus inside, just to cancel out this minus, because we can't, it won't be looking good. So that's why this minus goes away and it's the same. And what is the next step after this? Let's see. 2 mu over 2 mu. See, this 2 mu and 2 mu, they are, this thing is dividing. 2 mu is getting divided by this 2 mu. So these are both the same term, so we bring it here, so we can cancel out them, and in the upper part nothing remains, only 1 remains. And what is remaining in the down part, in the place of 2 mu we got 1, because this 2 mu cancel out with this, and plus 2 lambda square over mu, 2 lambda square over mu square, because we have this 2 mu. First we have to take the LCM of this, so 2 mu becomes here mu becomes into 2 mu, it's 2 mu square, 2 mu square. So this is the equation that we got. This is simple multiplication and division, nothing else. So this goes away, it remains 1 here, and here in the place here 1, and this 2 goes away, lambda square over mu square, right? Lambda square over mu square, it's just ending up, so be happy. Mu square plus lambda square over mu square. See, this comes here and this thing remains the same, and this mu square will be going up, so it becomes mu square over mu square plus lambda square. See, here is the equation. Pw of t is in the form of this way, and we know that a to the infinity is mtbf over mtbf plus mttr, and we also know that mu is equals to 1 over mttr and lambda equals to 1 over mtbf. So by replacing this pw of t into these forms, this is the formulas that we have, just to find out a working condition to the infinity, So just to find this a infinity, what we did, we keep the values, the pw of t equation into this form. Okay, so here it becomes aw to the infinity and 1 over mu square, right? So mu is 1 over mttr and square whole square, mu is 1 over mttr and whole square, plus lambda is 1 over mtbf whole square, right? So this square thing is going to solve out, and when it's solved out, what happens? See, when it's solved out, this is what we are taking. We are taking the LCM, mtbf square plus mttr square, and these things goes in multiplication, and this is this, and this thing goes up, it will invert, you know that, mttr square into mtbf square, and this thing remains here. The mttr square goes away, and what remains? mtbf square over mtbf square plus mttr square. So this is the aw to infinity. This is the equation that we got, and you know that we were talking about the series combination of two components. Yeah, the two components, we were talking about two components and they were in series. So obviously when they were in series and they were in two components, so obviously the square is valid. Yeah, this is square is mandatory, right? So that's why the square is coming here, and steady state availability of two components, two items in series. The formula for steady state availability is something like this, and we have proved it, and that's all for now. Thank you.